Welcome to today's deep dive session. If you're sitting in the studio right now at the Faculdade de Arquitetura...
Here at Universidade de Lisboa.
Right, exactly. If you're sitting there right now, you are probably designing a building that you think of as this permanent static object. Like you pour the concrete, you lay the stone.
You detail all the fenestration.
Yeah, and you just assume your creation is going to stand there as this unmoving monument against the elements. But I mean, under the brutal new realities of the European Green Deal, it's over.
It is entirely legally obsolete.
Exactly. If your building cannot actively sweat, if it can't mechanically breathe and operate as a localized power plant for, the electric vehicles parked underneath it, your design is already dead on arrival.
And that is exactly what we're tearing into today. We are looking at Professor Nuno Diniz Cortisos's lecture notes.
Specifically Lesson 06.
Right. From his Environmental Comfort and Energy Efficiency course. We're going to figure out how to make your architecture literally come alive. We're dismantling the illusion of the static building.
Because the transition we're mapping out today is an evolutionary leap. We are going from buildings as passive shelters, right, to buildings as responsive thermodynamic organisms.
And look, this isn't some distant, theoretical, avant-garde studio prompt. This is a survival guide for the immediate future. We are grounding every single theoretical concept today in the rigid, inescapable directives of the EPBD 2024.
The Energy Performance of Buildings Directive.
Exactly. And to understand why this shift is mandatory, we have to start by deconstructing what Professor Cortisos calls the Mediterranean paradox.
Oh man, I see this paradox just destroying student projects every single semester.
Oh, without fail.
Because, for centuries in Portugal, Spain, Italy, passive design was the absolute gospel. If you wanted to survive the Iberian summer, you built with massive thermal mass.
Meter-thick stone walls in the Alentejo.
Right. You minimize the fenestration on the south facade to limit the solar gain, and you prioritize cross-ventilation to, flush out all that heat with nighttime breezes.
And for hundreds of years, that passive delay of heat transfer, that was enough to keep the interior tolerable. It was a highly elegant, localized adaptation to a pre-industrial climate.
But then the paradox hits.
Right. The paradox is that the very same Mediterranean climate that perfected those passive traditions is now experiencing extremes that render passive design mathematically insufficient.
Yeah, because when the nighttime temperatures don't drop low enough to flush out that accumulated thermal debt from those thick stone walls...
Your thermal mass becomes a radiator.
Exactly. It just traps the heat inside. And under the new EPBD 2024 directive, which is just relentlessly pushing the entire continent toward NZEB...
Nearly zero energy building standards.
Right. And PEB... Positive energy building standards, relying solely on passive delay is a guaranteed failure.
Yeah.
Active systems are no longer a high-tech luxury, they aren't an optional budget item anymore.
They are mandatory.
So to frame this for you as you're sketching at your desk right now, think of traditional passive design as a phenomenally thick winter coat.
Okay, good analogy.
It's fantastic at slowing down the transfer of heat between your body and the environment. But a winter coat is, it's completely dumb.
Right, it doesn't react.
Exactly. So if you start running, your body generates massive internal metabolic heat, and the coat just traps it. If you cannot unzip that coat, if your cardiovascular system can't pump blood to your extremities, and if your skin can't sweat to dump that heat...
You'll literally suffer heat stroke while surrounded by freezing air.
Exactly. The passive coat becomes a trap. So your architecture now requires a cardiovascular system. It needs a heartbeat.
And that biological mechanism, that is the foundational blueprint for all architectural technology. Before we can even begin to talk about motorized facades or variable refrigerant flow systems, we have to look at the human organism inside the building.
Because ultimately, the only reason we enclose space is to keep the soft, highly fragile human inside from dying, right?
Yeah, basically, yes. The physiological basis for every single active system we engineer is the human thermoregulatory system. We are essentially designing a secondary macroscopic skin to assist the microscopic skin of the occupant.
And the human body is incredibly high maintenance. We're essentially walking metabolic furnaces that are just desperately working millisecond by millisecond to maintain a core internal temperature of exactly 36.6 degrees Celsius.
Right, and if the environment forces our core to drift even a degree or two away from that baseline, cognitive function plummets. Physical distress just cascades through the nervous system.
And eventually the biological machinery just shuts down entirely.
Exactly. Now, historically, the architectural and engineering communities attempted to measure and design for that 36.6-degree baseline using traditional steady-state comfort models.
Right, like Fanger's PMV.
Yes, the foundational text here is Fanger's PMV, or Predicted Mean Vote, which was developed way back in 1970.
And Fanger's model fundamentally shaped the last 50 years of HVAC design, but it carried this massive blind spot.
It treated the human body as a passive, steady-state recipient of thermal stimuli. It mathematically viewed the occupant as a static mannequin just sitting motionless in a highly controlled, hermetically sealed, artificially conditioned box.
It assumed we were just, meat sacks waiting to be cooled down by a machine. I mean, if the thermostat said 22 degrees, Fanger's model assumed everyone was perfectly happy.
Completely ignoring whether they were sitting in direct sunlight or, wearing a heavy wool sweater.
Which is crazy.
Yeah.
And that's why modern architectural physics, particularly in the context of NZEB standards, is completely abandoning the rigid steady-state approach.
Right. We are moving to the adaptive comfort model. The adaptive model recognizes the fundamental truth of human behavior, which is that occupants in naturally ventilated or free-running buildings are not passive victims of their environment.
They are active participants.
Exactly. If the ambient temperature rises, a person will shed a layer of clothing, they'll open a window to increase air velocity, they'll drink something cold.
And the adaptive model actually accounts for these behavioral, physiological, and psychological adjustments.
Which is huge because it actually broadens the acceptable temperature range and massively reduces the burden on our mechanical cooling systems.
But, okay, I was reading through Professor Cortiso's notes on how we actually quantify this, and I hit a bit of a wall with the thermodynamics. Cortiso's brings up the GAG two-node model from 1971.
Oh, right, the classic two-node model.
Yeah, and he starts diving into psychrometry and enthalpy. And look, I understand that sweaty cools you down, obviously, but how do those specific thermodynamic laws dictate what the building's active systems actually have to do to the air?
Well, let's break down the biophysics of the GAG two-node model because it is a masterpiece of thermoregulation modeling. GAG basically simplified the complex human form into two mathematically concentric cylinders.
Okay, two cylinders.
Right. The inner cylinder is the core. This is where your organs are constantly burning calories and generating metabolic heat.
And the outer cylinder.
That's the skin. This dermal layer is the boundary where that internal heat must be transferred to the surrounding environment via three primary mechanisms: convection, radiation, and most importantly for this discussion, evaporation.
Okay, so the core is the furnace and the skin is the radiator.
Precisely. But the radiator can only dump heat if the environment is willing to accept it.
Right. And the environment's willingness to accept moisture is defined by psychrometry.
Yes, psychrometry is the study of the thermodynamic properties of gas-vapor mixtures. So in our case, the mixture of dry air and water vapor inside a room.
So when your core temperature rises, your body pumps water to the surface of the skin, and this sweat must evaporate to cool you down.
But if the psychrometric conditions of the room are already saturated, meaning the relative humidity is pushing 80 or 90%, the air physically cannot hold any more water vapor.
It's like a humid August day down by Agus River. The air just feels heavy, your sweat just pools on your skin, and you feel entirely suffocated because the evaporative cooling engine has essentially stalled.
And the engine stalls because of a failure to transfer latent heat. Latent heat is the energy absorbed or released by a substance during a change of state, without a change in temperature.
Okay, break that down for the students.
So, when a microdroplet of liquid sweat on your skin absorbs enough thermal energy, it undergoes a phase change into a vapor. That phase change requires a massive amount of energy. The sweat literally steals that thermal energy directly from your skin, carrying the heat away into the air.
Wow, okay.
This drops your dermal temperature, which in turn cools the blood flowing just beneath the skin, which then returns to the core to lower your internal temperature.
It is essentially stealing energy to change state.
Yeah.
But, this relies entirely on the enthalpy of the room.
Right. Enthalpy being the total heat content in a thermodynamic system.
So if the air's enthalpy is too high, combining high sensible heat, which is the temperature we actually feel, with high latent heat, which is the humidity, the sweat cannot phase change.
Exactly. The heat remains trapped in the body. So when the psychrometric environment becomes hostile and the body starts failing to dump this heat, how do we quantify that suffering for an engineering standard?
Cortisos talks about the DISC index.
Yes, the DISC index. It stands for Predicted Thermal Discomfort, also developed by Gage. Instead of merely asking an occupant if they feel hot or cold, the DISC index mathematically quantifies the relative thermoregulatory strain required to restore equilibrium.
And it operates on a scale from 0 to 5, right?
Exactly.
So 0 would be thermodynamic bliss. The environment perfectly matches your metabolic output. Your core is at 36.6 without any conscious or autonomic strain.
No.
But walk us through a DISC index of 5. What is actually happening to the occupant's body?
At a DIC index of 5, the environmental conditions are deemed intolerable. Your body is in a state of severe physiological distress. Maximum vasodilation is occurring.
Meaning your blood vessels are expanding.
As wide as possible, yes, to push hot blood to the skin. Your sweat glands are firing at absolute maximum capacity, but the psychrometric conditions of the room are preventing evaporation.
Because the enthalpy is too high.
Right. Because the heat cannot escape, your core temperature begins to rapidly elevate above 36.6. And if this state is maintained, the occupant will experience heat exhaustion, syncope, and eventually heat stroke.
And this physiological reality is the absolute baseline of our architectural mandate. The entire purpose of the building envelope, the fenestration, the mechanical systems, it's all just to keep the occupant operating at a DISC index of 0 or 1.
But here is the massive constraint Professor Cortisos places on the studio. You have to achieve that physiological comfort while simultaneously minimizing the building's EUI.
The energy use intensity.
Exactly, and he provides a very specific benchmark. For well-insulated, high-efficiency structures in Mediterranean climates, the baseline cooling energy demand target is an aggressively low 12 kilowatt-hours per square meter per year.
Which is just, 12 kilowatt hours. That is a phenomenally low target.
It's a monumental engineering task. A standard, older commercial building in Lisbon might consume 50, 80, or even over 100 kilowatt-hours per square meter annually just to run the chillers.
So slashing that consumption down to 12 requires a total reimagining of the boundary between interior and exterior.
Mm-hmm.
The architecture cannot simply be a dumb box made of glass and steel anymore.
No, not at all.
Which means we have to design what the industry calls an alive skin.
Right.
To hit that 12 kilowatt hour target, the facade itself must become a kinetic, adaptive system. It requires electrical power to actuate mechanical movement based on a continuous feed of data from environmental sensors.
Sensors tracking solar angles, wind speed, internal temperature.
We're moving from static shading to active computational calculating.
And these adaptive facades are categorized technically as active systems specifically because they require that continuous electrical actuation to function.
Mm-hmm.
The primary goal is the massive reduction of incident solar heat gain during peak hours.
While simultaneously maximizing the penetration of diffuse natural daylight.
Exactly. If you block the heat before it enters the thermal envelope, your HVAC system inside doesn't have to burn electricity to pump that heat back out.
Okay, I am going to stop you right there because I see this in studio juries all the time. A student designs a beautiful sci-fi kinetic facade. It folds, it breathes, it tracks the sun perfectly in the rendering software.
Oh, yes.
But I am an architect, not an aerospace mechanic. If I design a massive commercial building with 500 individual motorized louvers on the south facade in a climate that regularly gets pounded by Atlantic rain and Saharan dust storms,
I know where you're going with this.
doesn't this just become a colossal maintenance nightmare? Are we trading energy efficiency for mechanical fragility?
It is the most critical question in adaptive design. The maintenance versus design dilemma, and the architectural history books are absolutely filled with spectacular failures.
Give us an example.
Look at the Institut du Monde Arabe in Paris, designed by Jean Nouvel and completed in 1987. It is widely considered a seminal moment in high-tech architecture.
Oh, the south facade of that building is stunning. It's covered in hundreds of highly complex metallic geometric diaphragms that operate exactly like the aperture of a mechanical camera lens.
Yes.
They were programmed to dilate and constrict throughout the day to optimize visual comfort and regulate solar gain. On paper, it was a thermodynamic triumph. But what actually happened in reality?
The mechanics failed. The incredibly delicate watch-like servo motors driving those apertures lacked the industrial robustness required for exterior architectural applications.
These just couldn't handle the elements.
They jammed with particulate matter and atmospheric dust. The maintenance protocols were far too expensive and complex for the facility managers to keep up with, so eventually the majority of those beautiful metallic irises simply froze in place.
And when the alive skin dies, the building suffocates. Because the facade could no longer dynamically block the heat, the building was forced to rely on brute force, highly energy-intensive mechanical air conditioning.
Just to keep the occupants from hitting a DIC-5.
Right, so the failed active facade actually worsened the EUI in the long run.
Nouvelle's building is the ultimate cautionary tale regarding the hubris of mechanical complexity. However, the industry has spent the last 4 decades learning from those exact material and mechanical failures.
So what's the counterpoint?
The counterpoint to the Arab Institute is the Kiefer Technic Showroom in Bad Gleichenberg, Austria. This building proves that kinetic skins can survive if they are engineered with industrial pragmatism.
Okay, the Kiefer Technic Showroom. It utilizes a mechanical folding facade consisting of 112 large, solid metal tiles that morph and pivot dynamically throughout the day.
But the fundamental difference here is the actuation. They abandoned the delicate Swiss watch aesthetic for 56 heavy-duty industrial electric engines.
Servo motors.
Exactly. Servo motors that are specifically rated for harsh exterior environments.
But the mechanical robustness is only half the equation, isn't it? Yeah. The thermodynamic success of the Kiefer building actually lies in its material science.
Yes, those folding panels are constructed from perforated aluminum that has been engineered to possess exceptionally high albedo values. The specifications dictate an albedo between 0.6 and 0.8.
Okay, let's make sure the physics of albedo are crystal clear for you listening. Albedo is a dimensionless measure of surface reflectivity.
Right.
An albedo of 0 represents a perfect black body, which absorbs 100% of the incident solar radiation and converts it entirely into sensible heat. An albedo of 1 is a perfect mirror, reflecting everything.
So by engineering those aluminum panels to an albedo of 0.6 to 0.8, the facade is physically reflecting 60 to 80% of the solar radiation straight back out into the atmosphere.
That radiation is rejected before it can ever cross the thermal boundary of the building envelope.
Exactly. And by pairing robust sun tracking sequences with high albedo materials, the data shows this specific kinetic system yields up to a 50% reduction in the building's air conditioning demands.
50%. That is massive. It's essentially a massive kinetic shield that intercepts the thermal load.
And we see a similar thermodynamic triumph using computational traditionalism in the Al Bahar Towers in Abu Dhabi.
Oh, right, where the architects took the traditional Islamic mashrabiyah, those intricate wooden lattice shading screens that have been used in the Middle East for centuries.
And they blew them up into massive, dynamic, computerized units that open and close like umbrellas across the curved facade.
But again, the success wasn't just the movement, it was the material selection. They didn't use wood or regular metal, they used PTFE-coated glass fiber mesh.
PTFE is polytetrafluoroethylene. It is the exact same synthetic fluoropolymer used to make Teflon.
Teflon.
Yes. And the selection of PTFE is critical for 2 reasons. Extreme durability against the brutal UV radiation and abrasive sandstorms of the Arabian Peninsula.
Which would destroy delicate materials.
Exactly. And the second reason is extremely high solar reflectance. If you build a shading screen out of a material that absorbs heat, the screen itself will heat up and simply re-radiate that thermal energy through the glass and into the building.
Entirely defeating its own purpose.
Right. But the PTFE mesh rejects the heat and stays cool.
And the performance metrics on the Al Bahar Towers are just staggering. By actively tracking the sun and deploying the PTFE umbrellas only where the incident radiation is highest, the dynamic screen reduces overall solar gain by more than 50%.
And by stripping that much heat out of the cooling load, the building saves an estimated 1,750 tons of CO2 emissions annually compared to a standard glass skyscraper.
1,750 tons every single year. But, motorized louvers and folding metal plates, they're still reliant on macroscopic mechanical movement. We're now entering an era where the concept of an alive skin operates at a microscopic molecular level.
We're moving beyond mechanical linkages entirely and stepping into advanced material science.
This is where we get into chromogenic or electrochromic glass. Products like sage glass. This fundamentally breaks the architectural assumption that you need a physical blind or a moving metal plate to block the sun.
Right. With electrochromic glazing, you have microscopic solid-state layers of metal oxides deposited directly onto the interior surface of the glass pane.
So when the building's environmental sensors detect excessive solar glare or heat gain, the automated control system applies a tiny, barely perceptible low-voltage electrical charge across the glass.
And this electrical current forces lithium ions to shuttle between the solid-state layers. When those ions migrate, the chemical structure of the metal oxide layer temporarily changes, causing the glass to visibly tint.
It transitions from perfectly clear glass to a deeply tinted, heat-rejecting barrier. And all of this without a single moving part.
None. You maintain the visual connection to the outside world, you eliminate the maintenance nightmare of jammed servo motors, and you control the solar heat gain coefficient entirely electronically.
It's solid-state kinetic architecture.
But if we want to fully comprehend how radical the shift in material science has become, we must conduct a deep dive into the Media-TIC building in Barcelona, designed by Enric Ruiz-Gelly and his firm Cloud9.
Yes, the Media-TIC.
This structure fundamentally redefines the physical anatomy of a building's envelope. Instead of utilizing heavy, high-embodied carbon glass panes, the building is wrapped in a technological skin made entirely of pneumatic ETFE cushions.
Let's talk about ETFE, ethylene tetrafluoroethylene, because the sustainable metrics of this polymer are absolutely staggering.
First of all, it's 100% recyclable.
Which is great. But the statistic that should completely alter how a student calculates their structural loads is its mass. An ETFE cushion weighs exactly 1% of the equivalent architectural glass pane required to cover the same surface area.
1%.
Literally 1%. If you remove 99% of the dead weight from your facade, the cascading effects on your structural engineering are immense.
Oh, absolutely. You need drastically less structural steel, drastically less concrete in the foundations.
Which result in a massive reduction in the building's overall embodied carbon before it even turns on a single light bulb.
But the ETFE cushions on the Media-TIC are not just static plastic bubbles acting as lightweight windows. They utilize an incredibly sophisticated shadow membrane logic.
Explain the shadow membrane.
So the pillows on the facade consist of 3 distinct layers of ETFE material. By mechanically altering the air pressure inside the different chambers of the cushion, the building's pneumatic system can physically push or pull the central layer, the septum.
And both the middle septum and the outer layer have a reverse printed pattern on them, right?
Exactly. When the central layer is deflated and pulled away, light passes through. But when the pneumatic system increases the air pressure, it forces the central septum to press directly against the outer layer.
And the printed patterns precisely overlap,
Instantly shifting the facade from highly transparent to heavily opaque. It is using pure air pressure to change the visual and thermal characteristics of the wall.
The most breathtaking thermodynamic mechanism, however, is located on the southwest facade. Because, as we know, the southwest orientation in a Mediterranean climate takes the absolute most brutal, direct, low-angle afternoon sun.
It's notoriously the hardest facade to cool.
Right. So to combat this, the Media-TIC does something completely unprecedented. The building literally injects a dense nitrogen-based fog directly into the interior cavity of the ETFE cushions.
Yes.
I want to break down exactly how this nitrogen fog limits heat transfer, because it isn't just a visual trick. It's not just the building, squinting. When you pump a nitrogen aerosol into that cavity, you are fundamentally altering the physical properties of the wall.
You are creating a localized, contained weather system.
Weather system inside the wall.
Exactly. The nitrogen fog acts simultaneously as a massive insulation barrier and a highly tuned solar filter. The dense particulate of the fog physically scatters the incoming infrared radiation.
Which is the wavelength that carries thermal energy.
Right. So instead of the infrared radiation passing straight through the transparent plastic and heating up the interior floor slabs, it hits the nitrogen fog and is scattered and reflected back outward.
It is thermodynamics as performance art, and the metrics prove it actually works. Because when the ETFE cushion is perfectly clear, it has a G factor of 0.35.
And let's remind the students, the G factor, or solar heat gain coefficient, represents the fraction of incident solar radiation that actually makes it through the window and into the building.
Right, so a G factor of 0.35 means 35% of the sun's thermal energy is entering the room. But the moment the sensors detect the afternoon heat spike and deploy that nitrogen fog, the G factor plummets dramatically to 0.19.
By dropping the G factor to 0.19, only 19% of the solar heat is penetrating the envelope. The global environmental impact of this single pneumatic system on that specific building is profound.
How profound?
By stripping that much thermal load away from the HVAC chillers, the nitrogen fog system prevents 114 tons of CO2 from entering the atmosphere every single year.
Every single year.
To contextualize that massive number, it is the exact carbon sequestration equivalent of planting 5,000 mature trees annually. That single active facade yields a 20% reduction in the total energy demands of the entire facility.
But okay, even with a G factor of 0.19, we have to face the thermodynamic reality.
Yeah.
19% of the heat is still getting in.
It is.
And you have the internal thermal debt that is constantly compounding. You have the computers running, the server racks generating heat, the LED lighting.
And you have hundreds of human bodies.
Right. Each radiating roughly 100 watts of metabolic heat continuously. So the ETFE envelope has done its job brilliantly, but the interior still has a thermal debt that must be paid. And to clear that debt, without ruining our target EUI of 12 kilowatt hours per square meter, we have to manipulate the air itself.
Which means we must transition from the exterior skin of the building to its internal organs. We have to examine the mechanical systems.
This is what Professor Cortisos refers to as the era of air conditioning 2.0.
Yes, and the absolute undisputed champion of this new era is the heat pump.
Now, if you are going to understand air conditioning 2.0, you cannot just draw a box on a roof plan and label it HVAC. You must intimately understand the physics of the refrigeration cycle.
Because the biggest misconception is that an air conditioner makes cold air. It doesn't.
Cold is not a substance. It is merely the absence of heat. A heat pump is a thermodynamic machine designed specifically to absorb heat energy from one location and physically transport it to another.
And to execute this transportation, the system relies on a closed loop containing a specialized chemical refrigerant and 4 primary mechanical components: the evaporator, the compressor, the condenser, and the expansion valve.
Okay, let's walk through the heating cycle. Extracting heat from the cold winter air outside to warm the interior. Step 1, the evaporator.
Right. Even if the outside air is a chilly 5 degrees Celsius, there is still ambient thermal energy present in that air. The liquid refrigerant passing through the outdoor evaporator coil has a boiling point so incredibly low that the 5-degree air is actually hot enough to boil it.
So the refrigerant absorbs that ambient heat from the outside air and phase changes into a low-pressure gas.
Exactly. Step 2 is the heart of the system, the compressor. This is the component that consumes the vast majority of the electrical energy.
So the compressor takes that cold, low-pressure gas and aggressively squeezes it into a tiny volume. And according to the laws of thermodynamics, when you drastically increase the pressure of a gas, you increase the molecular collisions.
Which drastically spikes its temperature. The gas becomes incredibly hot.
Step 3. The hot, high-pressure gas is pumped inside to the indoor unit, the condenser. The indoor air is blown across the hot condenser coils. The heat naturally transfers from the hot coils into the cooler room, warming the occupants.
And as the refrigerant bleeds its heat into the room, it condenses back into a high-pressure liquid.
Finally, step 4, the expansion valve. The high-pressure liquid is forced through a tiny microscopic orifice. As it bursts through the valve, the pressure drops instantly,
causing the liquid to rapidly expand and flash cool back to its incredibly cold starting state.
ready to travel back outside to the evaporator and repeat the entire cycle. It is literally thermodynamic alchemy. You are using electricity not to create heat, but to steal heat from the winter air and pump it indoors.
And this exact mechanical cycle is why Professor Cortisos makes such a massive point about geography. Portugal is the absolute thermodynamic sweet spot for air source or aerothermal heat pumps.
Because climate specificity dictates mechanical efficiency, right?
Exactly. If you install an air source heat pump in a Nordic climate, like Sweden or Finland, the system struggles immensely. When the outside air drops to minus 15 degrees Celsius, there is extremely little ambient thermal energy left in the air for the refrigerant to absorb.
So the compressor has to work incredibly hard, consuming massive amounts of electricity to squeeze whatever minimal heat it can find.
The efficiency plummets, but the temperate Portuguese climate rarely drops below 0 degrees Celsius in the winter and hovers comfortably between 10 and 25 degrees for the vast majority of the year.
And because the outside air is relatively mild, the compressor barely has to break a sweat to extract heat from 10-degree air to warm a room to 20 degrees.
And the mathematical metrics that prove this efficiency are COPS, the coefficient of performance for heating, and SEER, the seasonal energy efficiency ratio for cooling.
These metrics define the ratio of useful thermal energy provided relative to the electrical energy consumed. So if we look at a modern high-efficiency heat pump operating in the Portuguese climate, it regularly achieves a COP of 5.
Stop and think about what a COP of 5 actually means.
Yeah, let's break it down.
The machine takes 1 kilowatt of purchased electricity from the grid to run the compressor. Using that 1 kilowatt of power, the refrigeration cycle magically extracts 4 kilowatts of quote-unquote free thermal energy from the outside air.
It then combines the two, delivering a total of 5 kilowatts of heat into your living room. You are getting a 400% return on your electrical investment.
If you compare that to a traditional natural gas boiler, which maxes out at roughly 90 to 95% efficiency because some heat is always lost exhausting out the chimney, the heat pump is mathematically vastly superior.
However, a COP of 5 is only achievable if we pair the thermodynamic cycle with the advent of inverter technology.
Crucial point. Older, traditional air conditioning units utilized fixed-speed compressors. They were a binary machine. They were either operating at 100% capacity or completely off.
It was a nightmare for both the electrical grid and human comfort. The fixed-speed machine would blast freezing air into the room until the thermostat clicked off.
The room would slowly heat back up until it became uncomfortable.
And then the machine would violently kick back on at 100% power, causing massive power spikes. It is the mechanical equivalent of driving a car by flooring the gas pedal to hit 100 kilometers an hour, turning the engine off entirely until you coast down to 50, and then flooring it again.
It destroys efficiency. Modern inverter technology utilizes variable speed compressors. The inverter can modulate the electrical frequency, allowing the compressor to spin up smoothly.
So once the room reaches the exact desired temperature, the inverter slows the compressor down to a constant, ultra-low power idle state.
It continuously trickles just enough cooling into the room to counteract the heat leaking through the walls.
Perfectly maintaining a steady temperature without the violent power spikes. Empirical data shows that inverter-driven heat pumps are 30 to 50% more energy efficient than their fixed-speed predecessors.
But temperature is only one facet of indoor environmental quality. A building requires fresh air.
And the Portuguese legal framework is highly stringent regarding air quality, demanding exactly 0.60 air changes per hour, or H.
That means 60% of the total air volume in a given room must be entirely evacuated and replaced with fresh, oxygenated outside air every single hour.
The conflict here is obvious. I mean, if you spend electricity to heat a room to a comfortable 22 degrees, and then you simply open a window in the middle of winter to achieve your 0.60 H of fresh air,
you instantly vent all your expensive heat out into the street. You destroy your energy efficiency.
So to solve this, the heat pump must be integrated with a heat recovery ventilation unit, or HRV.
An HRV forces the outgoing, warm, stale exhaust air to pass through a highly engineered heat exchanger core at the exact same time that the cold, fresh, incoming air is passing through it.
The physical air streams never touch. They are separated by micro-thin plates of conductive material. But the thermal energy from the outgoing warm air physically transfers across the plates into the incoming cold air.
So you achieve the legally mandated 0.60 H of perfectly fresh air, but you capture and retain up to 90% of the thermal energy inside the building envelope.
It creates a nearly closed-loop thermal ecosystem. So we have the refrigeration cycle, the inverter technology, and the heat recovery. But how does an architect actually select the correct system architecture for their specific massing? Professor Cortisos notes that the selection between a VRF system, variable refrigerant flow, and a decentralized multi-split setup is entirely dependent on the building's volume-to-surface ratio, or VS ratio.
Yes, the VS ratio dictates how the building interacts with its environment. Let us analyze a sprawling, single-story logistics center or a long, thin educational block.
Okay, wide and flat.
This geometry has a massive surface area relative to its internal volume. It is highly exposed. It suffers from rapid, localized heat loss and gain through its massive envelope. The eastern rooms bake in the morning sun while the western rooms are freezing.
Right.
For this high VS ratio, an architect might specify decentralized multi-split systems, allowing each individual zone to manage its own distinct thermal loads independently.
But let's flip the geometry. Imagine a compact, 15-story corporate office tower in the center of Lisbon. This building has a very low VS ratio. Its deep internal core is completely isolated from the exterior climate, heavily insulated by the outer ring of offices.
Right, because of the massive internal heat generation from hundreds of employees, elevators, and server rooms, the core of that building likely requires active cooling 12 months a year, even in January.
Meanwhile, the executive offices on the glass perimeter are losing heat to the winter air and desperately need heating.
This is the exact scenario where a variable refrigerant flow, or VRF system, is mandatory. A VRF system is capable of simultaneously heating and cooling different zones within the exact same building using the same centralized compressor network.
So the system physically extracts the excess heat from the sweltering interior core, pipes that thermal energy through the refrigerant lines, and dumps it directly into the perimeter offices that require heating.
It moves the heat from where it is a liability to where it is an asset, drastically dropping the overall EUI.
Okay, I have to pause our thermodynamic utopian vision here.
Right.
Because as professors, we need to prepare you for the brutal reality of the construction site.
Okay, go ahead.
We are championing the pure electrification narrative here. We love the COP5 heat pump, but let's look at the actual urban fabric of Lisbon or Porto. We have hundreds of thousands of existing buildings deeply reliant on fossil fuel infrastructure, natural gas, or LPG boilers.
Yes.
The piping is already embedded in the masonry walls. The radiators are installed. If I am an architect doing a renovation, ripping out that entire hydronic system to install refrigerant lines and heat pumps is phenomenally destructive and prohibitively expensive for the average homeowner.
It's a huge barrier.
Furthermore, if you go to rural Portugal, deep in the interior, the electrical grid itself might not possess the capacity to handle the sudden massive load of thousands of electric heat pumps turning on simultaneously during a winter freeze. So if pure electrification is economically or infrastructurally impossible, what is the legitimate bridge technology?
That is an entirely valid pragmatic challenge, and it is a major debate within the regulatory bodies. We cannot simply bulldoze and retrofit the entire existing European infrastructure overnight. The transition requires a highly pragmatic bridge.
Right.
For rural areas or renovations where existing high-temperature radiator infrastructure must be maintained, biomass technology, specifically high-efficiency wood pellet boilers, offers a highly viable alternative. Under current European environmental frameworks, biomass is legally categorized as a carbon-neutral bridge technology.
Wait, I know students struggle with this concept.
Yes.
How can burning physical wood pellets inside a boiler possibly be classified as carbon neutral? You are actively executing a combustion process and releasing visible CO2 out of the exhaust flue directly into the atmosphere.
The carbon neutrality of biomass relies on the concept of the localized biogenic carbon cycle. Yes, combusting the wood pellet releases CO2. However, the exact amount of CO2 released during that combustion is mathematically equivalent to the exact amount of CO2 that the tree physically absorbed from the atmosphere via photosynthesis during its growth cycle. Okay.
As long as the forestry supplying the biomass is strictly and sustainably managed, meaning a new tree is planted for every tree harvested, the net addition of new carbon to the atmosphere over the life cycle of the forest is theoretically zero.
It is a cyclical loop. The tree pulls the carbon down, you burn the tree to heat your home, the carbon goes up, the new tree pulls it back down. This is fundamentally different from burning fossil fuels like oil, coal, or natural gas.
Exactly the distinction that matters. Fossil fuels represent ancient fossilized sunlight. That carbon was permanently locked deep beneath the Earth's crust millions of years ago.
Right.
When you pump oil or frack natural gas and burn it in a boiler, you are taking ancient sequestered carbon and injecting it entirely as new carbon into the current modern atmospheric cycle, permanently increasing the atmospheric concentration.
Biomass merely recycles existing surface carbon. It is an imperfect temporary bridge, but it is necessary while the grid modernizes to handle full electrification.
And speaking of the grid modernizing, we need to hammer home the final segment of Professor Cortisso's thesis. We have to wake the studio up to the immediate legal reality they are graduating into. You can design the most beautifully proportioned kinetic facade. You can calculate the psychrometrics perfectly.
But if you fail to comprehend the scale of the EPBD 2024 directive, your building cannot legally exist.
I frame this directive to my students as the legislative hammer.
The EPBD 2024 is fundamentally destroying the traditional boundary of what constitutes a building. Historically, an architect designed a standalone structure. It consumed power from the grid, it provided shelter, and its boundaries ended at the property line.
But the new directives mandate that the building must become an integrated, highly active node within a continental energy network. And the most aggressively disruptive aspect of this legislation is the forced integration of electric mobility directly into the architectural footprint.
This is the exact moment the panic usually sets in for a junior architect.
Break down the January 2027 deadline for us, because this is going to hit the construction industry like a freight train.
The legislation is explicit. Under the EPBD 2024, by January 1st, 2027, any existing non-residential building offices, commercial centers, universities that possesses more than 20 parking spaces must physically install and provide at least one high-voltage EV charger for every 10 spaces.
And for new residential constructions with more than 3 parking spaces, the architect must ensure pre-cabling infrastructure is installed for 50% of all parking spaces to accommodate future chargers.
Stop and calculate the physical implications of that.
Imagine you are designing a mid-sized commercial office park with a 200-space underground parking garage. The law now dictates you must physically install 20 active high-capacity electric vehicle chargers.
The electrical load calculations for your building just absolutely skyrocketed.
You suddenly need massively upgraded transformers. The transformer vault might eat up half of your ground floor lobby footprint. The electric vehicle is no longer a civil engineering or transportation issue that happens outside your building.
No, it is a massive parasitic electrical load directly tethered to your building's central nervous system.
But it is not just a parasitic load, is it?
No. The legislation is forcing the architecture to leverage that massive battery capacity. This leads to the ultimate realization of the active thermodynamic system, V2G, or vehicle-to-grid technology.
We are no longer just charging cars. We are utilizing the millions of lithium-ion car batteries parked beneath our buildings as literal decentralized power banks for the architecture itself.
Walk us through the 24-hour cycle of a V2G integrated building. How does the architecture actually use the cars?
So during the peak solar hours of the day, the building's massive rooftop photovoltaic array is likely generating far more electrical energy than the building's HVAC and lighting systems currently need.
Right.
Instead of bleeding that excess, highly valuable solar energy back into the municipal grid for a fraction of its worth, the building intelligently routes that excess power down into the parking garage, storing it in the massive batteries of the employees' parked electric vehicles.
The building uses the cars as a sponge to soak up the excess solar yield.
Precisely. Then the sun goes down. The solar panels go dormant. But the building's internal thermal debt still needs to be cleared.
The heat pumps need to run to maintain the internal temperature.
Instead of purchasing expensive, carbon-heavy power from the municipal grid at night, the building's smart meters reverse the flow. The architecture physically draws the electrical power back out of the parked cars, utilizing that stored daytime solar energy to run the compressors, spin the fans, and operate the alive skin.
The boundaries of our profession have completely dissolved. This officially merges the roles of the architect, the mechanical engineer, the electrical grid operator, and the urban planner into one massive computational discipline.
You aren't just designing a floor plan anymore. You're designing a localized, highly volatile power plant.
The building is now an active, breathing, energy trading node in a smart city grid.
Which brings us to the ultimate synthesis of Professor Cortisos's entire lecture. The historical journey from the heavy, passive Mediterranean stone box to the modern NZEB standard is a journey from the silent to the hyperactive.
To succeed in this new paradigm, you must master the microscopic thermodynamics of the human body, understanding the Gauge model, the DISC index, and the latent heat of evaporation.
You must scale that physiological understanding up to the macro level of the envelope, designing facades that fold, track the sun, and sweat nitrogen fog like the Media-TIC.
You must engineer internal organs driven by the COP5 thermodynamic alchemy of variable refrigerant heat pumps.
And finally, you must integrate all of those active systems into an electrified mobility network. It is an incredibly overwhelming amount of physics, legislation, and engineering to synthesize. But it is undeniably the most complex, vital, and exciting time in human history to be an architect.
Absolutely.
Which leaves us with a final, slightly terrifying but provocative thought for you sitting at that drafting desk right now, staring at your screen. If our buildings are now truly responsive organisms, if they breathe fresh air through mechanical louvers, if they sweat through evaporative nitrogen cooling to lower their G-factor, and if they store their biological energy in vehicular power banks,
at what point does architecture cease to be a construction discipline and become a form of synthetic biology?
As we begin integrating vast AI neural networks into these sensory control systems over the next decade, will your future buildings merely react to the environment as it happens? Or will they begin to anticipate it?
That is the absolute frontier of our discipline. We are moving toward a reality where an AI-driven building checks the meteorological data, recognizes a severe heat wave is approaching in 48 hours, and actively begins running its heat pumps during the cool of the night to aggressively pre-cool its internal concrete thermal mass, preparing its defenses before the heat wave even arrives.
It's learning. It is anticipating the threat and preparing its biology to survive it. So take that thought, look back down at your studio project, look at your passive stone walls, and ask yourself, is your building alive yet? Keep designing, keep calculating, and we'll catch you on the next deep dive session.